Hello and welcome to Handout 5, the last of the electromagnetic handouts. And before we move on to modern physics topics, so this is the last lecture or handout covering classical electromagnetism, and it is a culmination of many things we've seen before. The title you can see is Maxwell's equations, electromagnetic waves, and the Poynting vector, whatever that is, right? We'll talk about that. We have a few objectives. Understand that Maxwell's equations summarize all the laws of electromagnetism. That's kind of just a statement. You need to be like, okay, that's the big set of laws. Understand that Maxwell's equations can be used to determine the speed of light in a vacuum. That's one of the examples I'm going to show you. Understand that light is an electromagnetic wave with electric and magnetic components that are at right angles to each other and with a velocity direction that is found through the cross product of the electric and magnetic field vectors. So that's the... If you remember pictures, if you recall pictures of an EM wave and how it has that perpendicular sinusoidal shape for the electric field, and then a sinusoidal shape for the magnetic field, and they're perpendicular to each other, and then along an axis that's perpendicular to both the wave amplitudes is the direction of the wave itself. Well, it turns out that direction has a special name, and it's called the Poynting vector. Okay, and that's the third objective here, or fourth objective. Understand that the Poynting vector of an electromagnetic wave points parallel to the wave's velocity and represents the intensity of the wave. So those are in fact the units of the Poynting vector. All right, so going right into the key formulas, these are all formulas we've seen before, right? So because lectures 1 through 4, especially lectures 1 through 3, were all about kind of the building blocks leading up to this point. And so we've seen these are the big laws in electromagnetism. Now, we haven't exactly seen all of them, we haven't seen them in this form, so let's talk about what might be a little different, okay? Well, the first one is exactly Gauss's law, okay? So this is considered the first of Maxwell's equations. It just tells you that, right, summarize it. I won't label everything because you can refer to previous lectures for the labeling and the more full explanation, but it's saying that if you integrate around a closed surface, the net electric field going through that surface, which is to say the flux, because this represents the electric flux through a closed surface, then that must be equal to the charge enclosed divided by the permittivity constant. Okay, that's Gauss's law. Okay, so the other law that we have here is Gauss's law, but for B fields. Okay, so this is like the magnetic version of Gauss's law. It's something we haven't seen before because it's always just equal to 0. So there's really not much going on with Gauss's law for B fields as opposed to the electric case, which shows that it's talking about charge enclosed. Here it's just saying that there is no magnetic field enclosed, or that's not well, that's a thing, right? It's saying that there's no magneticism enclosed, but of course, because that's not actually a quantity. There's no such thing as magnetic charge, is there, right? And so sometimes what you'll see for Gauss's law for B fields, you'll see it summarized conceptually as just saying there's no magnetic monopoles. There's no such thing as particles that fundamentally have magnetism as a property in the same way that electrons and protons and other charged particles fundamentally have charge as one of their properties of that particle. And because of that, because magnetism is always created by moving charge, that means that if you have a closed surface, then there always must be as many field lines pointing out of that surface as into the surface. Thus, the flux must always be 0. Okay? So, kind of conceptual result, not something you would really ever use so much for actual like computational solving. Okay? So the next one is none other than Faraday's law. Okay? So Faraday's law we've worked with that quite a bit. What does it tell us? Well, it tells us that if we integrate the electric field along a closed surface, then what we're going to get is within that closed surface, so like a ring, for example, right? So if we're integrating the electric field along a ring, then passing through that ring is a change in magnetic flux per time. All right? So essentially the idea is if you have a changing magnetic field through a particular area, then along the perimeter of that area, that's the line, there will be an induced electric field, okay? And that, of course, can create a current, right? That's how we get, Lenz's law and the induction of currents, okay? So That's Faraday's law. Excellent. Okay. The last one, and we've seen this one as well, is Ampere's law. Now, what we saw from Ampere's law was the idea of integrating the magnetic field around a loop in order to find the current within that loop. All right. So it's kind of, I think of Ampere's law a lot like Gauss's law, because we're trying to find the thing inside of the surface. But of course, in Gauss's law, it's the surface. In the case of Ampere's law, you're trying to find the thing inside of the loop. So it's a line integral. You're integrating magnetic field of the particular perimeter, and you're finding the current within that perimeter. And that current will be running perpendicular due to the right-hand rule laws that we've been working with. So again, refer to previous handouts. But what the heck is this, right? This is new. We've never seen that second term there. So the reason that there is a second term is that's called Maxwell's extension. And what Maxwell's extension is all about is something that we haven't done computationally because it's quite difficult, having the two terms and really solving this. But it's pointing out the fact that you don't necessarily have to have a current in order to have a non-zero magnetic field. You just have to have a changing electric field. Okay? Now this is really this is the tipping point. This is where we're going to start talking about EM waves. Because I've often said this, right, that an EM wave is a self-propagating wave. It's created by a changing magnetic field. It creates a changing electric field, and the changing electric field creates another changing magnetic field, and so on. It's a chain reaction. Okay? Well, here we're really seeing that in equation form. We're seeing that you can get a magnetic field from a changing electric field, and you can get an electric field from a changing magnetic field. Okay? So then you might be like, well, why isn't there, an equivalent here? Why are these comparing Faraday's law and Ampere's law? Why is there asymmetry? Well, the same reason that there's asymmetry between the Gauss's law and Gauss's law for B fields. And that's that there's no magnetic monopoles. So you can't have a magnetic current. So there's no other case here, which makes Faraday's law kind of fundamentally simpler than Ampere's law with Maxwell's extension, which I suppose is why it kind of took, someone else revisiting, historically speaking, Ampere's law and adding to it, kind of finishing the story. Okay, all right, so last couple equations. The Poynting vector, okay, so this is the one I mentioned. This represents the direction. So as far as the vector is concerned, it just shows the direction of the EM wave. It's the direction of the velocity of the wave, okay? But its units are watts per square meter, okay? So the Poynting vector has units of watts per square meter. Computationally, it's done by taking the cross product of the E field and the B field, okay? And then just dividing by the permeability constant, okay? Which is just the 4 pi times 10 to the negative 7, all right? Tesla meters per amp, okay? So that's the Poynting vector. Directionality, I think it makes sense. The fact that those are the units would take a bit of digging, right? You got to really kind of work through, make sure you understand the units of the E field and the B field, and then you end up with intensity, watts per square meter. Of course, watts are joules per second, so you can really think of this as energy per time per area, right? That's what this is. That's what intensity is in general. And because the Poynting vector represents intensity, we can find the flux of the Poynting vector and its power. So if we have if we have an electromagnetic field passing through a known area, a defined area, then we can find exactly how much power is passing through that area, okay? And you could think there's obviously myriad applications of knowing the quantity like that, because then you can anticipate where the energy goes in a particular situation, okay? All right, so here we have, right, mostly a summary of things we've seen before with a few new additions to our familiar Faraday's law, Gauss's law, and Ampere's law, and definitely new the idea of the Poynting vector as the cross product of the electric field and magnetic field vectors. Okay, all right. So first thing I'm going to do is a pretty much straight up derivation. It's not so much an example, it doesn't have any numbers in it, but it's so important and interesting. And I remember being very captivated the first time I saw it at community college, in fact, that I just wanted to share it with you. Okay, so here we have example 1. Derive the speed of light from Maxwell's equations for the condition that describes a planar wave. Okay, so I put this in italics because it's kind of a jargon term. A planar wave is a region of space where the electric field and the magnetic field are approximately uniform. So that's all that a planar wave means. So it's really the simplest case. We have a uniform. So if you were in this chunk of space, this is probably like deep space or somewhere where there's not a lot of interference, you would see, as far as you would look, you would see a uniform electric field. So it would all have the same value, up, down, left, right. And everywhere you look, you'd also have a uniform magnetic field. Now, both those fields are going to be varying because they're waves, so they're varying in both space and time, but that everything is uniform, okay, spatially. Okay, and this would, okay, be a location very far away from any moving charge that created the electric and B fields in the first place. So we're not near any current. There had to be a current somewhere in order to create the EM wave, right? And specifically, it had to be a current that was either slowing down or speeding up, because you have to have an accelerating charge, not a constant velocity charge, to create a magnetic field, as we know, right? I hope. But we're so far away from it that those effects of change are gone, right? So we're so far away that everything is uniform. It's kind of like the difference between, like, if you were, very close to a very strong gravitational source, that gravitational source would have really noticeable direction. So if you move to the side, gravity might be pulling at an angle, but then if you lined yourself up with the object, then you obviously be pulling straight, being pulled straight towards it. But for example, on Earth, gravity appears to be uniform, right? So that's what we're looking for, right? That appearance of uniformity, that almost equivalence of uniformity. All right, so these are some pictures that we're going to work with here. I want to give a quick preamble to them. So first of all, this is a wonderful pictorial depiction of what I was talking about. Like I said, do you recall that picture of the perpendicular waves? Well, this is it, right? So the idea is that here the electric field is entirely in the XY plane. So you can see that the electric field, right, has amplitudes that are entirely in the Y direction. And then the magnetic field has amplitudes that are entirely in the Z direction. Okay, so it is in the XZ plane. Meanwhile, the direction of the wave, which doesn't come up in this problem, but the Poynting vector would point in the X direction. Okay, cross product. All right, and then there's a rectangle drawn on both of these, and what this rectangle represents is a loop. It's a closed loop, both for the purpose of doing, only for the purpose of doing doing flux. So we're going to do, we're going to consider the flux through that loop, and we're also going to consider the field integrated as a line integral around that loop. All right. So the important thing about the loop is that it's infinitesimally thin in the X direction. That's the direction that the wave is moving. This uniform wave, right? And it's given some arbitrary height, delta Y, to capture some of the amplitude of either the B field in the case of this loop here, or the E field in the case of that loop. Now, one thing about the loops is that delta Y is arbitrary and will cancel, so it's not going to show up on our results, because ultimately we're trying to find the speed of light after all. And it certainly shouldn't be a function of Y or anything, right? Certainly not. And furthermore, both the loops are going to be calculated, so the electric field and magnetic fields respectively are going to be calculated around the loops in the same direction. And so you can see based on the arrows that we're going in the counterclockwise direction for both of the rectangular loops. You see? Both of them are in the counterclockwise direction. That's key, because we have to do both of them in the same direction. And when we do, we actually get results that have negatives in the opposite places. But that's important. That's actually what we need for our result. But if we weren't integrating them in the same direction, we couldn't relate them in the way that we need to. Okay, all right. So that's a little bit of the preamble that I think is interesting and subtle, but I don't want you to feel like I'm making assumptions, but instead explaining the steps. Okay. All right. So speaking of steps, let's look at the beginning. Okay. So in this case, Maxwell's equations are. And again, this is the case of a planar wave. So this is uniform B field and uniform E field. Okay. So, Gauss's law is just equal to 0. Why is that? I mean, that's because we're so far away from the charge, right? So we're so far away from the charge that there's effectively no enclosed charge here. That's the whole point, right? We're like in deep space somewhere, and we're just picking up this faint signal that is like permeating out into the cosmos. Okay? Of course, there's no enclosed magnetic monopoles, because no such thing exists as far as we know. Faraday's law is unchanged, but Ampere's law has reduced to just Maxwell's extension, because there's no current anywhere nearby, so we can't form any loop in this region of space and enclose a current, because there's no such current to enclose. Okay, so this is our nice simplified version of Maxwell's equations specific for this uniform E and B field. Okay, moving on. And the wave function solution should look like this. Okay, So they should be E, because we've chosen to put E in the Y direction, and that means that B has to be in the Z direction. Now we could have put E in the Z direction and put Y in the Y direction, or put B in the Y direction, it wouldn't matter, but we've chosen these axes, and they have to be perpendicular to each other. Okay, but why do I even say that these are the wave solutions? Well, this is just something we know about waves, right? So first of all, we expect the solutions to these equations to be waves. Okay, that's a differential equation type of approach, right? We have an equation, we know a function is going to be a solution, and we assume that it's going to be this type of function. Okay, and what we know about waves, think sound waves. We know that sound waves are functions of both space and time. Okay, so x and t, or say a tension wave along a string. That's a function of both x and t. So this is a wave function form that you have seen before, I hope, or at least recall seeing. Okay, so because we're talking about waves, I'm going to then refer to some known quantities with waves, right? So this is all stuff that might not seem super familiar to you unless you remember studying waves particularly well. But this is all, I don't want to kind of reteach the ideas about waves and how we go from simple harmonic oscillators to understanding waves. But these are the kind of absolutely the most common results of that study, okay, which ultimately started with mechanics, right? Well before we ever talked about moving charges. Okay, so this is just something called the wave number, which is kind of like the angular wavelength. Notice like lambda is the wavelength, so it's just 2 pi divided by the wavelength. Okay, so that's called the wave number. This is angular velocity. So we got like angular wavelength, angular velocity. Those are, of course, it's always useful to do things in terms of angular quantities because then as long as you're using radians, you get nice clean results. All right, so of course, angular velocity is just 2 pi, angular frequency is just 2 pi times translational frequency. And lastly, the velocity of the wave is frequency times wavelength. And that's something that, at least that, if anything should sound familiar, that probably should. Okay? Okay, so wave basics out of the way. Now we're going to use Maxwell's equations, the idea that these are going to be solutions to these equations. And then from that, just that idea, find the speed of light, which is pretty remarkable. Okay? All right, so first of all, use Faraday's law. That's this one here. Okay, so all I'm going to do is I'm going to do one side of each equation at a time. And in fact, I'm only going to use Faraday's law and Ampere's law with that Maxwell's extension. We're not even going to need these ones because they're just zero. They're not doing anything. We don't have to worry about them. Okay? So if we just look at the left-hand side of Faraday's law, that's the line integral. So if I take the line integral, let's think about this. Well, the components of our little chosen rectangle, the two components that are perpendicular to the electric field won't produce anything from the integral, because in the integral is a dot product. And anytime you take the dot product between two vectors that are perpendicular to each other, what do you get? Zero, of course. So the only parts that will survive the dot product are components of the electric field that are parallel to our chosen rectangular loop. So that's just going to be these components here, okay? Well, let's think about we chose to go in the counterclockwise direction, so let's think about the two components, okay? The parallel components. So here, this section, the direction that we're integrating around our loop, the direction that we're doing our line integral, is actually going to be perpendicular to the electric field. So that's going to be negative. That's the negative E times delta Y, okay? This other section, this one over here that's pointing up, well, that one points parallel to the electric field. So the dot product should give us a positive. Just think that when you take the magnitude of the dot product, it's like multiplying by cosine of the angle between the two. Of course, cosine of 0 is 1, cosine of 180 is negative 1, okay? But why do I have E plus delta E? Well, because over here, where the loop and the electric field are parallel to each other, thus positive, then we see that the electric field is slightly stronger, isn't it? And since it's slightly stronger, the electric field will be whatever the electric field strength was over on the left-hand side of the loop, plus a little bit more strength, right? Because we're closer to the amplitude point. Great, okay? So when we actually finish that integral with the two sides, right? The parallel and anti-parallel sides, we end up just with the dE times delta Y because the E cancels. All right, so there we go. That's the left-hand side of Faraday's law. Meanwhile, on the right-hand side, and here RHS just stands for right-hand side, we have negative uppercase phi sub b over dt. What's that? Well, that is just the time derivative of the magnetic flux, okay? So if I'm interested in the magnetic flux through the same loop, it's got to be the same darn loop I talked about on the left-hand side of the equation. It's this loop right here. Well, how much magnetic flux is there? Well, look, the magnetic field is moving perpendicular to that loop, so there is flux passing through there, so it's definitely non-zero flux. And it's going to be some time-dependent magnetic field passing through that loop, won't it? Okay? So indeed, we get a time-dependent magnetic field passing through that loop. And so it's going to be, because flux, remember, is just BdA. And so here it's just going to be the field, which is time-dependent, so it doesn't come out of the derivative. But the area is time-independent, so it does come out of the derivative. And the area is simply width times height. So just dx times delta y. Okay? Now notice my notation from here to here, I went from a derivative to a partial derivative. That's because here flux, we didn't really define what flux is, so I can just kind of leave it as a derivative as a definition. But over here, we know full well, based on our proposed solution, that the magnetic field is definitely a function of two variables. And here we're only taking the derivative with respect to time, thus partial derivative. Okay, so now we're just going to combine the left-hand side with the right-hand side. Okay, that's all I do here. This is just combining the two results, so the left-hand side and the right-hand side. Right there, as you can see. Delta y cancels out because it should be independent of whatever rectangle we chose. Okay, we could have chosen at any point, in other words. All right, and we'll clean this up a bit more, and there we go. Okay, so here's our final partial derivative relationship. So why have we even done this, right? Well, we've done this because now we're in a place where we can plug in our proposed solution. Okay, because we couldn't very well plug that into the integral and really get a meaningful answer, right? So the whole point was to take Faraday's law and Ampere's law with Maxwell's extension, clean them up a bit, that's all we've really been doing, okay? So that then we can put in our proposed solutions and then find the constraint on those solutions, which ends up being the speed of light. Again, pretty cool, right? Okay, so let's go ahead and do the same thing, but now we're going to do it with Ampere's law, okay? So kind of rinse and repeat. Okay, so use Ampere's law with Maxwell's extension. Okay, so here it is. I'm then again do one side at a time, so I'll start with the left-hand side. I'd make the same sort of argument that I made before by doing the line integral. In other words, the perpendicular components don't do anything because the dot product it just zeroes them out. Here though, notice that the parallel part is actually the shorter part of the rectangle, or it's the side of the rectangle that's closest to the weaker magnetic field, and the anti-parallel part of the rectangle is the part that's closer to the stronger magnetic field, closer to the amplitude point of our sine wave. So that's so interesting, right? Because I told you, I kind of set you up for this because I wanted to make sure that doesn't seem weird, or at least like seems weird, but seems like there's a reason for it. Because again, both loops are counterclockwise. But if look at this, because they're both counterclockwise, that means that you have opposite sides that are parallel to the amplitude, right? It's kind of, just looking at the figure, you kind of have to do a double take to be like, I guess that's right. And it's just one of these amazing things about kind of 3D functions and cross products, and really kind of, there's these little subtle phenomena that happen like this that I think really kind of stretch your visualization tools of thinking about 3D systems. I just think it's so amazing. Okay? So this simplifies in a very similar way to the Faraday's law one. It simplifies to just dB times delta Z. In this case, there's a negative, okay? And again, that's because of that whole 3D nature. Okay, and then the right-hand side of Ampere's law of Maxwell's extension, well, that's just going to be kind of just the same sort of flux argument. The area is time independent, so it just comes right out. And then all we're left with is the electric field that stays inside the derivative because it is time dependent. Okay, and so then we set the two sides equal to each other. We cancel out the delta Z. All right, notice that now the negative came from the left-hand side then instead of from the right-hand side, but both times it did give us a negative. So then we get this result. So notice how these two results are so similar to each other. Okay? So I put them both in green boxes. Okay, so now we're going to use the results from Faraday's law. Or we'll start with Faraday's law. So using the result from Faraday's law and substituting our wave function solutions, what we get is this. Okay? So all I've done, zoom out a bit so you can see. So all I've done is just substitute in the wave function. Okay, so every time there's a B, I put in the wave for the B field, for the magnetic field. Every time there's an E, I put in, I'm using this one. Every time there's an E, I put in the wave function for the electric field. Okay, and then I'm just going to take the derivative. So I'll take the derivative of this function with respect to x. I'll take the derivative of this one with respect to t. All right, and when I do that and take care of the negatives, I get this. And the negative cancel, because both the derivatives would become negative cosine, but in this case, thinking kind of about what's and what, we see the negatives cancel out, and we're left with this function. The k came out because of the chain rule, and the omega also came out because of the chain rule, okay? So that means that you can cancel out the cosine, and in other words, or another way to think about this is we need omega and to equal something so that this is true for all values of t. So again, think of like last week. Think of of solving those equations, those differential equations, and then finding the value of omega, the value of angular frequency that made the solution true for all values of t. That's a big deal that I focus on a lot. Same thing here, right? So this is the constraint that makes the proposed wave function true for all values of time t. Okay, and the constraint ends up being omega over the wave number is equal to the electric field magnitude over the magnetic field magnitude. Okay, and it also turns out omega over k is just v. And again, we can easily derive that by just thinking about our definitions up here for waves. Okay, so that's the constraint from Faraday's law. Now we're going to do the same thing with Maxwell's extension of Ampere's law. All right, again, use direct substitution. All right, so I just do the derivatives, clean up the negatives and the chain rule and all that business. There we go. All right, so then what does that tell us? If that solution is true for all values of t, then this must be the case. Okay, so now I have these two constraints, and now they both have a v in them, so I'm going to combine them. So, all right, so finally combining the constraints on both solutions, I end up with just mu naught epsilon naught v, so permeability, permittivity times velocity equals 1 over velocity. Well, why is that? Well, because look, here it is. Here's the permeability, permittivity times v equals b naught over e naught. Well, look, b naught over e naught is the same as 1 over v, right? If I just take the reciprocal of both sides here, right? And I take v to the negative 1 power and this to the negative 1 power, well, of course, that just flips the denominator with the numerator, and we get b naught over e naught, okay? So then there's the combination. Now I'm just going to solve for v. When I get v on one side, isolated it, I get v squared, take the square root of both sides, all right, plug in the numbers, and we got the speed of light. There it is. That is where the speed of light comes from, okay? That's kind of the idea of that we empirically have these fitting constants, the permeability and permittivity constants, and those two fitting constants of the universe dictate the speed of light, okay? Or you could think of the speed of light as being the overarching constant that has these ones underneath it. Okay? All right, so I'm going to go ahead and make a second video for the second example to wrap this up. All right, so thank you for watching, and please tune in to take a look at that second example. And in that second video, I'll also mention a little bit some tips about kind of how you can approach the homework problems.